So when do y'all running with timers? Anybody timers? Huh? Well, in your personal life, timers. Where y'all running the timers at? Anybody got a microwave? Garage door light? Yeah, some garage door lights when you walk in, when you pull in, they'll turn on, and then after it stay on a certain time, and they'll turn off. Car lights, car headlights. Most new cars have headlights on them. Like mine, I leave mine on all the time. Cause why? They cut off automatically, right? Except when I pull in my neighborhood. When I pull in the road, it goes. My lights shine right in my neighbor's windows, so I'll turn them off because there's a big street light out there anyway. Uh, Dome lights automatic. My car. Uh, yeah, huh? If it's a time test, there's a time going on, right? Microwave ovens, washing machines, dishwashers. You know, all these guys have got what on them? Timers. Toasters have got a timer on it, right? You understand that? So we run into timers all the time. So if you run into timers all the time in your life, you know it's going to be a lot out there on industry where we're going to have a need for timers. So we're going to look at what we call non-retentive timers. First of all, we got two categories. We got off delay and on delay timers. And what would you think? So an on delay timer is going to start timing when the rung goes true. An off delay timer is going to start timing when the rung goes false, which is basically what your headlights do. My dome lights, right? You understand? So when it goes false is when it does that. Then we have what we call a retentive timer and a non-retentive timer, and this is true on most PLCs. I know the S7 software for Siemens has these two categories, or retentive and non-retentive. We're going to pick up a new output instruction called move, which is a very, very powerful instruction, really powerful. One of the big things a computer can do is just literally move things around, move binary information from this location to that location or vice versa. So every programming language that I've ever seen supports some type of move instruction. Connect timer instructions together, interlock them. So y'all have all seen flashing lights and stuff like that. We'll see how we can do that with timers by interlocking. And then cascading, which means when this one finishes timing, it'll trigger another one to start timing. And that way you can get extremely long timers because we're limited to the amount of numbers we can put them on. Most of them, and we'll talk about that in a minute. But most of them are little. Most timers, especially Adam Bradley's, are limited to a 16-bit number, which means 65,535 seconds. Well, what if I wanted a timer that would go for 2 weeks, right? You understand? Then what we could do is we could have one timer do what? Trigger the next one. We call that cascading. Fixed timers, variable timers. I've never seen a fixed timer. Well, I don't guess that's true. And that's motion detectors. Anybody got a motion detector in their house? Usually when it triggers it, but that's not fixed too, because usually you can set it like 5, 10, 15 seconds after there's no motion. Variable timers, almost every timer I've seen is I guess most of the timers in your car would be fixed timers, which means you can't do what? You can't change that. You can't change the time. Right? How long your lights stay on after you get out of your car and close your door, right? How long your radio plays. So when I turn my car off, if my radio's on and my doors are open, my radio stays on for a certain amount of time. But as soon as I open the door, what does it do? It goes off. Single input timers, which is what we have. Double input timers is what Siemens prefers. And we'll look at those. But these are the electrical symbols for an electrical timer. So if we use the PLC to trigger a timer, then this would be the symbols we would use. Okay. So if it points toward the contact, these are going to be what? On delay timers. If the arrow points away, it's going to be an off delay timer. So this would be on delay, right? Normally open on delay, or some people say normally open timed close. They would call this a normally closed timed open, right? They would call this a normally open timed open because it's off delay. This would be a normally closed timed close. So your off delay timers, you say the same thing twice. Your on delay timers, you say it opposite every time. That makes sense? Okay. So these are the electrical symbols for the timer contacts. The relay coil for a timer, so all a timer is basically, well, most of our timers, we have different type of timers. We have what we call dashpot timers, which basically has a diaphragm that's full of a liquid. And then when we energize it, it's got a spring that tries to push it into another diaphragm. And what you do is you control the size of the orifice that the liquid goes through. And these are called dashpot timers. And these are still all over the place. They're very, very simple. So this is a dashpot timer. So this is my timing element right here. This is where I adjust the time. So all you're doing is adjusting the orifice between the two diaphragms. Does that make sense? So how fast can the liquid flow from one side to the other, which would be the time. And so this is my relay. So this is an on delay timer. I'm sorry, this is an off delay timer. So notice when I hit it, the contacts change instantly, right? You understand? But when I de-energize the relay, can you see it took time? Yeah, in fact. So what I just did is I'm increasing the time. So here, the contacts changed instantly, right? You understand? Right? You understand? So a normally closed would open instantly, right? So this is why we say normally closed, timed closed. So it would go back closed after a certain amount of time, right? So this is an off delay timer. And there's the relay coil. And here's the time, and here's the adjuster, and there's the little switch. This is an on delay timer. So you can see the timing element, actually the timer. So the actual timing element is over here. And then we have a solenoid, which we still call a coil, right? So here's the coil. And then when I put whatever's required by this coil right here, this is a 110 volt coil. So it's AC coil. I put 110 volts across here, then it would cause the solenoid to pull in, and then you can see it start doing what? Yeah, because it's turned down pretty. And then sooner or later the contacts, well, either all your normally open would change and your normally closed would change, right? Does that make sense? So this is an on delay timer. We have what we call synchronous timers, which use a synchronous motor. You'll see these used a lot in older applications. This is the way we would do it with motor controls, right? You understand that? Of course, if we can do it with motor controls, we should be able to do it with a PLC. So this one's got a dial on it, people like, and then we can come up here and we can set times with a dial, right? Understand that? And then this shows you all the contacts. So this actually has a motor back on the back, and this would be all the contacts that it controls. So that would be 1, 2, 3, 4 pole double throw. So one thing about mechanical and motor controls, you're limited to the number of contacts a relay can have. Inside a program, how many contacts can a relay have? If it's software, somebody say a lot. Yeah. Mechanical, we're always limited to the number of contacts that we could have. This is one of the biggest ones I've seen, a control relay. I think some of the contacts are missing off of it. So this is a control relay that I passed around a certain time. And look at the size of this thing. And this has got 1, 2, 3, 4, 5, 6, 7, 8. So this would be an 8-pole single throw relay. So we're limited to the number of contacts we can put on a mechanical relay, right? This is our force, by the way. So this would be a normally closed contact, and you have to specify, or you have to rearrange these. You can take these off and you can make it normally open and normally closed, but that's mechanical. So if you need to change a contact on a relay, what would you have to do? You'd have to go out there and do it on the relay. How many of y'all have used the wrong contacts in your PLC program? Using the examine if closed when you needed a what, right? So every one of y'all has made that problem. All you do is go into the software and change it, because the relays inside a PLC program are not real. They're software. And what do we mean by software? You can change it, right? So this is a control relay, and it's got 1, 2, 3. So my timer, my timers in motor controls are going to have a certain number of contacts, right? You understand? But you could use a timer to bring in a control relay, right? You understand that? And maybe increase the timer that way. Then we have solid state. This is a neat timer because it's both a time delay open and a time delay closed. It's an on delay timer and off delay timer. So it's got 2 timers mounted on each side. So it's got 2 timers. So when we energize the coil, one of them on this side would be an on delay. This guy over on the other side would be a what? An off delay. So this is a neat timer. Now more and more what we're moving to is we're moving to solid state timers. Now what advantage does solid state means electronics, right? What advantage does these guys have over those mechanical timers like that? Yeah, no moving parts. So that guy we can fail 2 different ways. We can fail electronically or electrically, or we can fail mechanically, right? This guy can only fail one way. So this is an off delay timer. All I do is to set the time, I just turn a little knob right here. We have programmable timers. Well, we have different types of timers. A programmable timer is you tell it what type of timer it is, whether it's an off delay or an on delay, or retentive or non-retentive, or a cycle timer, or what other timers that we have. I didn't show you a cycle timer, a mechanical cycle timer. No, I'll find it. No. This is a programmable timer. So what does that mean? Yeah, so what I passed around was an off delay timer, but the off delay timer would always be an off delay timer, right? So if I had a bunch of off delay timers and an on delay timers, and I kept spare parts, and I'd have to keep all these spare parts. If I had a timer that I could program to be a what? Off delay, on delay, retentive, whatever timer I need, then all I would do is keep one spare part. So this is a programmable timer. So we use this dial right here to set the type of timer that we want, and then we set a multiplier, and then we set a time. So this is a programmable timer, and this is solid state. This costs a lot more than off delays though. So this guy right here is not cheap. And on the side shows you how to wire it, by the way, if that makes any sense. If you take the sensors class, we'll play around with those. I think sensors is required in both degrees now, I think. Sensors are very, very important. So these are all mechanical timers, or these are what we would use in motor controls. The problem there is that these are basically hardware, right? You understand that they're not software, which means, so if I see all these timers and I understand I need all these timers, then of course you've got to understand we need to have the ability to program these things inside our computer. So here's our 2 categories. We got either what? So what is an on delay? It starts timing when the rung becomes true. An off delay will start timing when the rung becomes false. Everybody understand that? Does that make sense? So like I get in my car, my radio's playing, I turn my ignition key off, my radio keeps playing. It plays for a certain amount of time and then it turns off. So that would be an off delay timer, right? You understand? I get out of my car, I leave my lights on, I turn my ignition key off, I get out of my car, and what happens? After a certain amount of time, my lights turn off. So those would be off delay timers. On delay timer start timing when the timer coil is energized, or in our term, I like to say when the rung becomes true, right? Normally open timer, contacts closed, normally closed timer. And this is what's nice about a software timer is you can make as many normally open and normally closed timer contacts as you need. If you buy one of these guys, you're dedicated to what's in there, right? Solid state timers usually have very few contacts. They might have one normally open and they might have one normally closed. So on a solid state timer, if you need a bunch of contacts, you're going to have to run it through a control relay that's got a bunch of contacts. Timer contacts, so it says normally open, contacts closed, and normally open when the timer is finished what? Timers. Timer contacts immediately revert to their normal state when the timer accumulator register resets to 0. Now this is definitely PLCs. Those guys don't have accumulator registers. Those guys either have diaphragms that it pushes right a liquid from one side to the other, or it's got a synchronous motor that runs in synchronous with it, or it's got solid state devices that generate our time. Inside our PLC, we're going to have something called an accumulator. It's just a software timer. And what do you think the accumulator is going to do? It's going to show you the time. Yeah, so it's going to actually show you while the timer's running. Delay before contact switches when the timer turns on. No delay when switching when the timer turns off. So it's a on delay timer. So that means when you energize it, time is going to take place. When you de-energize it, the contacts are going to change back to their original state instantly, right? Y'all understand that? Off delay timer, start timing when the rung becomes what? False. Everybody understand that? So timers are output instructions. We need to make sure. So the timers are going to go on the L2 side, right? Everybody understand that? Can you put more than one timer in a rung? Yes, they just have to be in parallel. You can't put two of them in series. One timer per line. We can have multiple timers in the same rung, right? Y'all understand that? So it's an output instruction. Timers contact. So on an off delay, when you energize or make the rung true, all the contacts change instantly. When the rung becomes false is when you have the what? When you have the time delay. Everybody understand that? Contacts revert to their normal state when the timer accumulated register resets to 0. So some, like Siemens, like to use two input timers. They got a timer and then they got an enable. So what happens is your timer would time it and then it would stop and you would reset it with a what? With the enable. Allen Bradley uses single input timers. So that means you enable it and you do what? And it starts timing at the same time. And then when you disable it, it's going to reset the accumulator. A coil format. That's what I wanted to do, but I couldn't remember how to change over to ladder. A coil format would be basically it would look like an output, but then it would have a special symbol for timers. So we'd have a coil, and then we might have a time, right? That would enter the time. That makes sense. But it would be a coil format. More and more, they're going to a function block format for timers, and that's what RS Logic does. So we're going to have a block for a timer. We're not going to have a coil. I'll try to show y'all that the RS Logic's next class. So we're going to use the function block format. It uses a box shape to display the time instruction, more common symbol for displaying timer instruction, and this is true. So I think step 7 for Siemens, their COIL, TIA, the Total Integrated Automation Package, TIA, gives you an option of using the COIL format or the block format. 500 though, RS Logic 500 is the block format, so that's the one we'll look at and figure out how it works. So we got these registers. We got what we call the preset register inside the timer. And what are we going to do with the preset register? This is where you're going to put the number that you want it to time to. We can put it in. What's the difference between a constant and a variable? In programmers, anybody know? So we deal with constants and variables. Put them back on the table. Thank you, Mark. So in numberings, what's the difference between a constant and a variable? Yeah. And a constant is so pi would be considered a what? A constant. Or we in electronics we use a 0.707 a lot, and especially when you start dealing with DC, that would be considered a constant. In programming, a constant is something that you have to change the program to change the number. So constant and variables are numbers, right? And the book will throw this term out every once in a while. They say operands. This comes from you got to understand in PLCs, PLCs came up through the computer community. So a lot of the jargon that we use is what we've used in computers. So in machine language program, we call the binary code that we use to tell the processor what to do, we call that an operational code, or they call it an opcode. The number that the instruction is working on, they call that the operand. So you'll see that in this book. It'll pop up every once in a while. So when they start talking about operands, these are the numbers that the instructions are working on, right? You understand that? So in this, your operands can either be constants or they can be variables. So in programming, a constant is a number, an operand that to change, you have to change the program. A variable is a number that we can change, that changes without changing the program, right? Y'all understand that? Does that make sense? And we'll show y'all an example, especially the way I can input. I can preset this register from an input port, or I can put a number in there. But the preset register holds the number that you want to time to or from, right? You understand? Time. That makes sense. Then we have the what? The accumulator. What does the accumulator do? Yeah, it shows you, and this is what the instruction is looking at to see when the timer's finished, right? When the accumulator meets its value, right? Does that make sense? Or 0. So what we do is we put a preset register in there. Let's say 100, and when we start it, it'll start at 100. Then it'll go to what? 99, 98, 97. And then when it gets down to 0, that's when the timer says it's done. And then the status register or the flag register, we've got some access to this, but we're not going to look at this very much. We'll look and see what access we have, and it's a little neat that we'll look at it. But this holds the status of the counter, right? So in Allen Bradley, so if you're dealing with the 1000 PLC, you've got T4. So every timer starts off with T4. That's the data file. If you're dealing with the 1100s, T4 by default, but you can use anything from 9 up to 255. So you could have a T10, but it's got to start with what? T. So all your timers start with T. So that's what your instruction will start off with. Everybody okay? And we're going to be dealing with bytes. So we're going to say T4, right? I'm sorry, we're going to say T4 colon, and then we're going to give it a number. And the number can be anywhere from 0 to 255 because it's an 8-bit number. Everybody okay? That makes sense. Timers can go from T:0 to T:255. In theory, it can have up to 256 timers. In practice, the number of timers is limited by the PLC memory. Some Allen Bradley PLCs allow data files 9 through 255 to be used as timers, but it's still going to be limited by the number of amount of memory you have there, right? Y'all understand that? So if I'm dealing with the 1100, it allows us to do that. I might have a T8, but it's going to start. All of them are going to start off with what? T. That makes sense. So the book says T4, but that can change. But it always boils down to how big can your programs be? Determined by what? The amount of memory the PLC's got in it. That's what determines the size of your program. How much user memory you have, right? That would be awful. You got a big old program, you buy a bunch of PLCs, and you're on your 99th line, and you run out of what? Memory. Your 99th rung, excuse me. Let's see, multiplied by a preset. So Allen Bradley uses what we call a preset, and it's a it's called a multiplier, or it's called a time base. Let's look. Let's make sure. So we'll actually. So I'm gonna pop up my RS Logic software, and I'm gonna come up here and I'm gonna create a new program. First thing it wants me to do is what? Check the CPU. Okay. And of course, this one we would come in. This is a 1100 B. Oops, I went right past it. This is 1100 Series B. Where's the information at? It's on the side of the PLC, right? On the side you cover up, by the way, when you put extra modules out there. So that's something you need to remember. You need to get that number off there before you start mounting modules on the side. Then the next thing I would do, if this guy here had had additional I/O strapped on the side, then I would go over here to I/O and I would tell it what modules we had on strapped to it, right? You understand that? So this is a hybrid PLC. Okay. Now, if you got a modular PLC, you've got to do that, right? You'll remember that. Okay, then we're going to come up here and we're going to insert a rung, and then we'll insert an input so we can see it. And this is our palette of instructions. So I'm going to go to timers, and we're going to do T on. What do you think type of timer that is? Yeah, it's an on delay timer. And I'm going to drag it back down, and it pops over to the output instruction side. It's a one lead. It's a one input instruction. So this one lead coming in, the one input, not only starts the timing, but it also does what? Disables it too. And we'll see. We'll reset it. So I come up here. I got to give it an address. So we're going to start off T4, right? You understand that? And then I'll put :0. So there's my timer. Oops. I think I put no, I did. Okay. Then the next thing it wants to do, and this is what people don't understand, and this is what Allen Bradley does, is when you hit enter, it pops up, but it puts you up in the comment column, not in the symbol column. There's a lot of difference between a comment and a symbol name, right? You understand that? Y'all see what I did? So you're going to have to click on that symbol column. Okay, so we've given that a symbol. Now the next thing that is called a time base. This is our multiplier. So right now, here's my preset. So I'm going to come up here and put 100. And I've got a multiplier of 1. So this is going to time for what? 100 seconds. But these are the multipliers available. So I've got a .001. So now it would time for 1 second, right? You understand? And then what's the last we have here? A .001. So now it's time for 100 milliseconds, right? So this is a multiplier that we come up with to come up with our time base. So let's don't do it that long. Let's do 10 seconds. Got a multiplier of 1. Now I think on the 1000s the time base is fixed, and I can't remember what it is. But if it's fixed, like at 0.1, it's probably 0.1 if it's fixed, because if it was 1, you couldn't do milliseconds, right? You understand? So I think it's 0.1 it might be limited to. And then you're going to have to multiply everything. So if you wanted the time for 10 seconds, you would put in 100, right? You understand? So here's my preset. Here's my accumulated value. It's on delay timer. Let's assign this to input 0/0/0. Give it a symbol. Okay. Are we okay? Come up here, check it for errors. Looks okay. What can I do now? Yeah, I can download it. It's asking me for the time name of it. And it says I don't have permission, so I got to go to, even though I'm the administrator of the computer. So I'm going to put it on our file server. Download the program, switch to the run mode. Okay. And we go online. Okay. So we're going to come up here and we're going to close switch 1. It's already closed. Okay. Can you see what it's doing? Now notice, so we're using the enable and the time for one input. Some timers they have an enable and they have a time. So what would happen is it would time out and then it would stop, but it would stay there until you did what? Until you reset it, right? So here's going to close. We got it set up. We got it set for 10. We got a multiplier of 1, a time base of 1, so it's going to time for 10 seconds. Now this is what's very important over here. These two status registers that they give us call for, one of them's called enable, one of them's called DN for done. Y'all understand that? So watch, as soon as I enable it, the EN will go true, but the DN, which is the done, will not go true until we reach our preset time. Wrong switch, Rich. Yeah, well, we'll do that right now. So here it comes. Now notice, enable still true, everything stops, and then the done call went true. Okay, that makes sense? Well, the timer itself is energized. It's just that the done doesn't energize until it's done. Okay. So what we could do, though, is we could come up here and we'll insert a line down. We'll insert another rung right here. And then I'm going to use a contact, and I'm going to call it timer 4, right? Colon, T4, I'm sorry, 0/done. It's a bit, right? You understand that? So what we just did is addressed what? This coil right there. And then we'll come on and we'll turn on the light with this. Okay. Of course, I know there's no arrows. And then we'll do what? Download it. It's asking me for a revision number. By the way, if you give it a revision number, then it'll give it a different file name. So you not only have your original, now you have your what? You have your backup. Okay, y'all can't see my light, but y'all can see when this becomes true, right? So what I'm going to do is I'm going to, so as soon as I turn the switch off, it resets itself, right? Okay. I'm going to turn it on. Then after 10 seconds, that done coil is going to go true. It's going to close this contact right here, and then my light will come on. See it? And it's going to stay set at my preset value until I do what? until I disable it, right? Which means, like I said, this is a single input timer. So the input, that one input is not only telling it to start timing, it's also a reset. That makes sense? Pretty neat. So we can go any value up to 65,536, but then we can change our multipliers. If that's not enough, I'm sorry, 65,535, right? You understand? 65,535 because it's a 16-bit number. If I need something longer than that, I can cascade it. So I can use the done bit of this one to do what? Start the next timer. So we could time for a year. So they call that the time base. I need to redo this so I don't have to look it up again. Time base. The available multipliers depend on the what? The PLC. So a lot of your fixed PLCs, you have no option but to use the multiplier or the time base that they have. This one has 3 time bases you can choose. I think that guy there's got 4, I think. We're not going to fire it up to look. The enable bit, now this is, they do this the same way. So we have an enable bit that basically we're using that at the same time, right? You understand? Then we have a bit in there called timer timing, which does not give us a contact, but it's available to us. So when I start the timing, this guy would become true, and when it stopped timing, it would do what? Come false. And this is the timer timing bit. That's available to us. This is the way we address it. We'd start off T4 or whatever number. If we assign it another number, we're going to use T4. Then this would be the timer number, right? You understand? And then we would use the TT, and that would use our timer timing bit. This is what we'll use for cross-couple timers, and we'll see that when we get into that. And then, of course, we understand the done bit, right? The enable is available to us. It's the one that's up on the left. So anytime the timer is enabled, that output's going to be true. You okay? This makes sense? Lost anybody? 3 different types of timers in Allen-Bradley 500. This is also true. We got a non-retentive on delay. We got a retentive on delay. And then we have a non-retentive off delay. So what would you think about the retentive? That means when you disable this sucker, it's going to hold its time. The only way you're going to do is we're going to have to pick up another output instruction called what? Reset. And we'll see that in a minute. So we've already looked at this, okay, here? So here's that enable. These are already out there. Here's the enable. This is on anytime this rung is true, this guy right here is going to be true. This guy is only going to turn true when your accumulator matches that number right there. So what would we got a multiplier of 0.01, so what would this timer time to? Okay, you okay? 5 seconds. We okay? The move instruction, this is an extremely powerful instruction. The move instruction, this is an output instruction. It's used for copying the contents of one data file into another data file, or for loading numbers into data files. So we can load the preset with this instruction right here. We can preload the accumulator with this instruction right here. We can't change the time base, but we can load it. So this would give us the ability to come up with a variable, right, instead of a constant. Yes. So usually we use these multipliers to get times that are not equal numbers of 1. So if I wanted 1.5 seconds, I can't get 1.5 seconds with the 1. So if this was the next one, then I would enter 150, right? And then I would use this multiplier right here, and that would give me a time of what? 1.5. The Siemens is understood to be milliseconds. But if you end the time with an S, it's understood to be what? Seconds. So if you don't specify S, if you don't say, 100 S, then it considers it to be milliseconds. So you can do that. I think step 7 is always milliseconds. The new TIA portal allows you to enter seconds or milliseconds. Are we okay? So this is using the move instructions. So here they're moving 1,000 and they're putting it into the preset register, right? You understand that? By the way, and this is where that period comes into play. The preset register is a word. So the slash is telling us it's a bit. A dot tells us it's a what? It's a word. The preset register is a word. Now, can y'all see the address there? So let me make it bigger. So this address right here, they're saying T4, so that specifies a timer, right? Then they're putting colon, timer number 0, and then they're putting a dot, which means what follows is a word. Because the preset register is a word, right? Y'all understand? So if you put slash preset, then you're going to get an error on that rung that you can't clear, right? You understand? Until you say, I'm going to load this word out there. The preset register and the accumulator register are both words. 16 bits, right? Everybody understand that? So that's why if we any 16-bit register, we have to specify it as a word. We don't take for granted. Are we okay? So here they're moving, Here they're moving 1,000 into the what? Into the preset register. Here, when we click this, they're moving what? 1,500 into the preset register. So that would make this a what? A variable. Because now, if I hit switch 1, I change my preset register without changing the program. If I hit switch 2, I change the preset register without changing the program. Right? You understand that? A while ago, if I was to come up here and change the preset register, that would be considered a constant because I'm changing the what? Literally changing the program. So I could come up with all types of variables, but I'm going to show you something really cool. So this is figure what? 8-2. So here's that program right here, right? If it works, sometimes they have problems in these programs. So I'm going to change these to switches. So they're using what? Switch 1, switch 2, and switch 0. Just make it easier for them to deal with them. Okay. So we'll go to run. So notice when I hit switch 1, I could change that to a push button, right? Now look at the preset register. What's the preset register got in it right now? And we need to change that. So let's, because it's already got 100 in it. Here they're going to preset it with 64 hex. 64 hex, which is what? It's 100. So this is why you specify hex, is you just enter your number with what? H. So here he's going to preset it with 96. So let's do that one first. And that's hex. So that switch what? 2. So see, the preset register went to what? 150, which is 96. If I press this one right here, which is 1, the preset register goes to 100. You see that? So what it's doing, it's taking this number. This is my source. This is my destination. Source is where the number's coming from. Destination is where it's going to, right? You understand that? Okay. Are we okay? And then this would be the preset register. And of course we start timing with 0. Are we okay? Now let me show you something cool. If this lets me do it. No, it's not letting me do it. Oh yeah, input 0. So what I'm doing here, so let's download it. This is a simulation. I hope it'll let me do it. No, this don't work. I have to do it with the real PLC. Oh, no, duh. Somebody say duh. So 0 is my control. So y'all want to go duh together? Duh, Rich. So let me go to input 3. 3.0, right? Because I want to input the whole word. Oops. Oh, can y'all see what I'm doing? So this right here is a binary 7. So that, and I'm going to come over here and load it. And I just loaded mine with 7, right? Well, that would be a binary 15. So I'm going to come over here and load it. So this is truly a variable, right? You understand that? So my source can be anything. So what I've done is I've addressed a whole word of my inputs. So I've literally addressed this whole word right here because I used the dot, right? Input 3 dot, right? And then I can come over here and do what? So you could have a little switchboard on there and the person could be doing what? Yeah, but you have to be able to go from, well, that's not true because that is converting the decimal for us. So that's the power of the move instruction. Is people think we can just move numbers into there, but we can actually get those numbers from all different types of places that comes into that move instruction. So that move instruction is very, very powerful. So how does it work? So what's the source? That's where that data is coming from. It could come from the output of a math instruction. So you could take the answer of a math instruction and store it in here, right? You understand that? It could be the output of a compare. It could be an output of a logic instruction that we're not doing in this class. And then you could use that to set up the preset on or the accumulator. You could change the accumulator if you wanted to. So let's come in here, and here we're going to, what would be the address for the accumulator? Anybody remember? ACC. So you have access to the accumulator, you have access to the preset register. You don't have access to the time base. You can't change the time base. So that's going to be a constant, right? And then now when I come over here and hit switch 2, did I download it? Then what we're going to do is change the contents of the accumulator. No, it didn't either. It should. So I'll have to check on that, guys. This is a simulation. He doesn't do things. He does all kind of weird stuff. So he does this. It's a good program, and like I said, for $45, you can't hardly beat it. But he'll let you get by with this, and I can still do what? I can still download it to my PLC. Huh? RSLogix won't let you get by with putting two outputs on the same row. So it's a good simulation. You just gotta understand its limitations. Okay, we're almost through with this, and then we'll take a break, which all of y'all are waiting on anyway, right? And we'll get to the lab. You're not going to have a slightest idea how to do this because you were sleeping in class. Reset instruction. So when we deal with a retentive timer is going to hold its time even when it's disabled. So the only way you're going to return the timer back, the only way you're going to reset the accumulator is by using a reset instruction. So when we look at our, is this RSLogix? Yeah. So when we look at our timers, there's this guy right here. See what it says? It says what? Yeah. So here's T on, that's an on delay. TOF, that would be what? And then RTO, what's that? That's a retentive on delay timer, right? So once this guy right here, so we'll do a constant. So we'll call this what timer? T4:1. Everybody okay? Okay. And then give it a symbol. We'll call it timer 2. And then we'll control this with the same input. And just see okay. So we got this guy controlled by the same input. Of course, what didn't I do? Well, we'll show that in a minute. I didn't put a time in here. Okay, so here's switch 1. Here's switch 0. And they both start timing, right? I'm going to set the time for 10 seconds. The bottom one, timer done. Are we okay? I'm going to come over here and turn switch 0 off. The top timer, it reset to what? 0. The bottom timer stayed at 5. Because it's a what? It's a retentive timer, right? I know y'all need a break, guys. So hold on. So we're gonna put another rung in here. Here we'll use a different switch. So here we use input 0/1, and we'll call it reset. And then over here in our timer instructions, we'll use the what? Reset instruction, and we want to reset T4 :1. Okay. Of course, I could have typed in timer 2, or started typing in timer, and then we'll download it. Okay, so here comes switch 1. And the top one starts timing, right? I say that. It's going to time to 10. The bottom one's going to time 5 seconds. It's done, right? I take switch 0 back to 0. The top timer automatically resets. The bottom doesn't. I'm going to hit switch 1, and then it resets it to 0. So this is a retentive timer. So a retentive timer, if you use a retentive timer, you're going to have to do what to it? You're going to have to reset it, right? A non-retentive timer, as soon as you disable it, it's going to reset. Okay, I'll take a 10-minute break. Right. So off delay. So here's our off delay. That's the only one we're really looking at. So right now it says it's met its preset and the done is false. You understand that? Okay. And then we would come up here when we make it true. Okay. Nothing happens, right? And it says it's done. It went to 0, right? Okay. And then when I turn it off or make the rung false, this is when it starts timing, which is what you would normally use, right? So an off delay timer, you would want something to be on until it times out, right? You understand that? Are we okay? Everybody okay? That's what it is on my car. So instead of, I said that wrong. So we'd use a normally open contact because it would be true until it meets its time, and then it would turn whatever I want off, unless I want it to work anyway. You can use normally opens or normally closed contacts. It's up to you on which way you go, right? You understand? Everybody okay? Okay, cross couple. So cross coupled. This is where we can set a time. So let's look. This is next. So we always flash things. We always do stuff like that. You know, I've got a program I wrote that one thing about Logic Pro is it gives you tasks that you try to design a program around. So it comes with a lab book, which is really neat. And you'll start off by controlling a garage door. And then it says, okay, we want to flash lights, and you figure out how to make lights flash while it's in motion. Then it figures out how you do it. If something blocks it, what do you need to do? You know, if this sensor says something gets in its way, how to make it stop the door. So it's a really neat application for $45. It just lets you get by with a lot of stuff that you can't get by with. So like if I was in high school and I can't buy a PLC, it would be a good program for a high school to have to teach PLCs without having a true PLC. Okay, so cross couple. So let's look at cross couple down, and this is where we create flashing lights and that kind of neat stuff. Interlock timers. I call them cross couple, but interlock. So can you see what they do? So this is normally closed on timer 1, and then timer 1's got timer 0 normally closed. So when I close my switch, timer 1's going to start timing, right? This guy's not going to start timing, but it's soon understand. But when it Then it's going to come up here and do what? Flip this over, and it's going to flip that over and flip that over. So what's it going to do? So what? How long is it going to flash? Anybody can figure that out? Huh? Well, it's actually going to be 1 second. It's going to be on for half a second and off for half a second. So we got this in RS Logic. So I think a Logic Pro. I'm not going to put it on my PLC because where is it there? So this is the cross couple, and y'all can actually see it working. Can you see it? Oh, I keep wanting to do these switches for this switch. All right. So as soon as I turn this on, this is going to start timing. This is going to open. So the other one resets like that, right? You understand? And then when this times out, timer timing goes false. This guy closes. This guy starts timing. This guy's false, right? You'll see that. So this is what it looks like. So what could we do with this? Well, anytime you're in industry, you see a lot of what? Flash of lights. And this would be the basic circuit that we do that with. There's another way I can teach you that's a lot easier in advanced PLCs, but we're not going to do it in that this time. Please, no. Now here's the light flashing. Flashing for 1 second. If I want it to flash longer, I would just change the watt. I would just change the preset. That makes sense? See how that works? Everybody okay? So we do this in PLC 3. One of the things they do is when you pull the E-stop, what they want to do is they want lights flashing indicating that it stopped. By the way, E-stop don't necessarily turn off all your outputs. E-stop should do what? Turn off all the outputs that could do what? Hurt people. So over there, if we do the E-stop, you'd see the lights on the front would start flashing. We use 2 of them, by the way. One of them's off while the other one's on, which would tell somebody that tell an operator that the E-stop button had been hit. Then we do what we call cascades. What's cascade? Yeah, and the one in the book is wrong, by the way. Cascading. Timers are cascaded together such that one timer finishes time and the other one starts. And this is the figure I have. If they hadn't changed it, this would never work because they're using what? Yeah, they're using normal close. So what you want to do, you start the first one. When it's done, it goes true, and it starts that one. When it's done, it goes true. Does y'all's book still have the normal close in there? Y'all got the new book. Some of y'all got the new book. So timers, still chapter 8, right? This is figure 8.8-6. Do they still use? They got the open, so thank goodness they made the correction. So y'all's book is correct. The old book is wrong, so I need to correct that. Oh, where did Logic Pro go? Oh, wait, I see it. I think it's this guy right here. I tried to renumber them. It's numbered wrong on mine. Nope, that's not it. That's the one I just had. So which one was that one? That's the one I just had. So that was 14, right? So it must be 15. Okay, so here we go. So this is right. So they got this set. So we'll go ahead and download it, switch to run. So the switch is already closed. So you can see the top timer slapping. How long is it going to time? Yeah, 250. As soon as it gets 250 done, goes true, it's going to close this contact over here in rung 1, which is going to cause the timer 2 to start timing. So it's what? It's done. This guy's going to start timing. It's going to time to what? 300. When he gets through, it's going to get done. It's going to time this. It looks like they're leaving all the lights on, but y'all see how you can cascade those to get more time than's available to the actual the preset register. So the preset register is a 16-bit register. So that means the biggest number you can load in there would be 65,536. So if you use the multiplier of 1, then you'd get that many seconds, right? You understand? But if you need more than that, right, then you would come up in, so how many seconds in a day? 60 times 60 times 24, right? But we could get timers for days, right? You understand? Days. So that would be the way we would do that. Are we okay? Mr. Rose trying to figure it out over there. Yeah, so 2 days would meet the limit on one timer, right? I don't know. We don't need that. We don't need to know that, guys. It'd be okay. So that's it on timers, guys. Very straightforward, right? So we got two categories of timers. What's the two categories? On delay and off delay, right? Y'all understand? How much was it? So we couldn't time for a day, right? But we could do it with multiple timers. 60 times 60 times 24, right? Or 60 squared times 24 for math geniuses. So then we have two types of on delay timers. We got what we call a non-retentive timer and a retentive timer. What's the difference? One resets when you disable it. The retentive timer, you have to reset it with a reset instruction, right? Reset instructions come very important when we get into counters. So let's go to chapter 9 and finish up on counters. Have two types of counters. What's two types of counters? No. No, you're taking timers. We can count up. Oh, we can count down. So we got two types of counters. We got up counters. We got down counters. The Allen-Bradley does not support up-down counters. Siemens does. So you got a count up and a count down input. Here you would have to mathematically do it, and so we're not going to teach how to make an up-down counter with math. So we can have coil timers, which Siemens Step 7 does, or we can have single input counters. So we use single input counters. Now, what would you think what would you think the counter would do when it reaches its maximum count, or its preset count? Excuse me. I wouldn't want it to do that, because you could accidentally say, well, I want an indication when we get to 50, but for some reason it runs 55, and you want to reset when it gets to 50. Well, you would lose those counts, right? You understand? So no, none of your counters reset automatically when they reach they'll give you an indication when they reach their count, but then they'll keep counting. So what do you think you have to do to all your counters to set them back to 0? You have to reset them. Good. That's good. And down counters in Allen Bradley are weird, guys. So you get rid of up counters are straightforward. Down counters are weird. I don't like doing this. So let me just. We got the worst network over here. Counter input instruction, counter output instructions are similar to timer instructions displayed in foil or coil format. And of course, we're using what we call the block format, right? Function block format. A single input, we got a single input counter, which means we don't have an enable input. We either got count up or do what? Count down. For every pulse on the input, it's going to count either count up or count down, depending on what type of counter we're using. When it reaches its preset value, it's going to keep counting. Right? You understand why? Because you wouldn't want it to lose a count just because you said I want 50 and something goes wrong and 55 gets through there and you've lost 5, the counts of 5. So all your counters have to be what? Reset. Counters for the 1000s are going to be C5. For the Micrologic 1000 or the 1100s, you can use C5. This one's built in, or you can use any one between 9 and 255. But you're going to have to keep up with those above 5, right? Above 8, right? You understand that? So if you decide to use T, if you try to use 9 for timers, you can't use 9 for what? Counters, right? You understand that? So it's up to you now to control your memory. Up through data file 9, the PLC controls that, which should get 8 up to 8, which would be floating point numbers. The PLC controls that. If you're on the 1000s, that's all you got. If you're on the 1100s, then you got access to all these guys. So we can have a lot of counters. So what basically determines the number of counters you can have in most PLCs is how much memory you got in the PLC, right? Count up, count down, accumulated value increments for every change of the input signal. Count downs the counter decrements, right? Whenever the counter input devices change state. Make sense? It's real hard. We okay there? I need to throw it up on full screen, Don. We have what we call the preset register. This is called, we address it as C5, then we're going to give it a number, or C whatever, C5, we're going to give it a number, dot preset. It's a 16-bit register. We can load it, we can put a constant in there, or we can load it with a variable, with an input instruction or a move instruction, right? Everybody understand that? Your accumulator value, we address that as C5 or whatever. We're going to use C5 in this class, C5. Then the counter number, every counter's got to have a unique number. We put a dot, why dot? Because the accumulator is a word, right? Y'all understand that? We okay? Holds the accumulator count number. The status register holds the flags that are used by the PLC to keep track of the operation of the counter. We got some weird things that's coming on here. Well, it's not weird to me. It might be weird to y'all. We've got to be able to represent, and we'll look at this in a second. So we have what we call the count up bit, true when the up counter is counting, right? And then we have a count down bit that's available to you, that every time you count, it's going to do what? It's going to go true. Everybody okay there? And then we got the big main done bit, which tells us what? The accumulator is equal to or exceeds the contents of the preset register. And this is where it really gets weird with down counters. Are we okay? The problem we have is that we're dealing with binary numbers, and we've got to be able to count down, or we got to be able to count up, which means we got to be able to represent negative numbers. It's a 16-bit number, guys. Now, I'm not going to teach you how we do it, but I use a method called 2's complement to represent signed numbers. But what you do is you sacrifice the most significant bit to indicate the sign of the number. If it's a 1, it means the number is negative. If it's a 0, it means the number is positive. So as soon as I sacrifice one bit, then I lose. I don't get 65,536 combinations anymore. I get 32,768 or 32,767 because 0 takes up one of your positive spots. Because zeros would be 16 zeros, right? And it has no weight. So that's why when we deal with signed numbers, we'll always have one more negative than we do positive. That makes sense. So that means we've got to have a way of knowing if I exceed the range of the counters. So these counters cannot count up higher than what? Up counter cannot count up higher than, it's going to count, but it's going to change signs. So what'll happen is it'll count up and it'll flip over to a negative number, which is not good. So we have a bit in there that we would monitor called the overflow bit inside the flag register that indicates if it's a negative number and it flips over to a positive because we exceeded the range, or if you have a positive number and it flips over to a negative because you exceed the range, it would come up and set that bit. So if you know you're going to do that, you need to monitor that. Now we can cascade counters too, right? You understand that? So I could set one up to count in hundreds, and every time it's done, it would increment another counter, right? You understand? So we could cascade counters and get any number of count we want. It's just on the Allen-Bradley PLC, the maximum positive number I can have is what? 37,767. The maximum negative number I can have is what? 32,768. That makes sense? Yes or no? You're looking kind of fun. Did I say 37,000? 37, because it's 64. 37,000. Thank you. 37, which would be half of 64. 64K, so 37. What's that? Well, it's half. So take your calculator out and put 10 to the... yeah, I think that slide is wrong. Because I have those numbers in my head. So 2 to the 2 raised to the 15th. Where's my raised to at? Y to the X. Right there. 2 raised to the 15th, right? So it's 32,000. So the slide is wrong. So I was saying the number right in my head. Probably is. I'm probably the ones that did the slide. So thank you. So I said the number right, but it was wrong this time. 32,767, 32,768. Because that's what I was saying, right? 32,000. That's wrong, yeah. And you're right. It's half of 64 should be 32. Once the counter accumulator matches or exceeds the preset value, the done bit output is set. So this is the guy we're going to use most of the time when the counter meets its value, right? The counter will continue to what? Count. A reset output instruction must be used to reset the accumulator to 0. To move a move instruction can be used to set the accumulator to any value. Not only can you set the accumulator to any value, you can also set the preset to any value. Oops. Preset. Present. Everybody's present. Right? So the preset register, this is the way you would address the preset register if you're going to load it with a variable. If you're going to load it with a constant, you just type it in, right? Y'all understand that? If you're going to load it with a variable, then this is what you would use this. Or if you wanted to pull it out, you can move the contents of the preset register into anywhere you want to. The accumulator would be addressed like this. So C5, then we would put the counter number, right? And then we'd put a dot accumulator. The count up bit, this is the way we would address the count up bit, which indicates the counter's counting. We would use what? So the count up is a bit, right? You understand that? So this would be C5, and this would be the counter number, right? And then we'd be count up, count down. But this is the guy we're going to use most often in this class right here. Is the what? Done bit. Are we okay? So this is the counter. This is the count up. They got it set up. What's the preset value? 10. Is this a constant or a variable? As a constant. I would have to change the program, right? You understand? I would have to go offline, I would have to bring it up, and I would have to change its preset value. So this would be considered what we call a constant. So we'll do this with Logic Pro, which is so much easier to do that. So we'll go to what? New. Oh, can't do that in program mode. So I'll go to new. New. What's the first thing we need to do? Logic Pro works with all of them anyway, because it's a simulation. So we'll use MicroLogic. Then I would do what? Add a line, right? Okay, so I need to get back to my offline to get my, on this one. So I'd add a rung, right? Oops. I like Logic Pro. You can just keep clicking on them. We're going to need 2 rungs, right? We're going to bring what we're going to count. We're going to put that right in here. Here's my counter instructions. We're going to count up, right? Okay. Then we'll come up here and we'll use another input. Oops, wrong thing, Rich. We'll put another input. Then over here, now you can't use a coil as a reset. You got to use this reset instruction, right? You understand that? Okay. Well, I see people use coils for reset, right? So we'll call this count. Oops, I'm sorry. Input colon zeros. No, I'm sorry. 1/0. I keep forgetting which PLC I'm on. Okay. Then we'll reset it with input colon 1/1. Okay. And we'll change these to push buttons. What counter do we want? We're going to give it a count. We're going to call it C5 colon like 0, right? Oh, not CR. C5 colon 0. Preset, what do we want to count to? Okay, so we'll count to 10. Okay. Down here, what are we going to reset? We're going to reset C, right? C5 colon 0. Are we okay? That makes sense? Then we're going to go online. We're going to download it. And then we're going to switch it to run. Okay. So I'm going to come up here. Counted what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The done bit went true. Now notice the count up is flashing every time I hit it, right? Okay. Went true. We'll keep counting. Notice it just does what? Yeah, it just keeps counting. By the way, RS Logic doesn't do Logic Pro doesn't do an overflow, so I can't demonstrate that to you. Well, it could be a limit switch. It could be a photo detector. It could be anything that gives us a click or gives us input when whatever we're trying to count goes true. You'll see a lot of what we call it through the beam photo detectors, where they shoot a light beam across from a transmitter to receiver, and when something flies by there, it gives us a count. Or it could be a limit switch with a whip on it, or it could be just about anything that's going to give us true. We got to have a true to false, true to false, true to false, true to false, right, to count. So if I wanted to count a push button, I could count a push button. But keep track of how many times somebody hits the stop button every day to take breaks. But notice it keeps counting, right? Y'all see that? It keeps counting. Okay, and how are we going to make it? How are we going to clear it back? So notice the done bit is set if it meets or exceeds what? The count value. Y'all understand? Okay. All right. And then I'll come back and I'll reset it. Okay, then the accumulator went back to 0. Everybody okay? But I can address the preset register and I can address the accumulator register, which means I can load a timer with whatever I want to. So I might be running boxes and I got a 24 box and I got a 12. Well, all I have to do is just preset my calendar into what? Either 24 or what? 12. So I can address that preset register. I can address the count. I can address the accumulator. So I could clear it by storing 0 in there. Besides using a reset, that's another method we could use to clear it. But the reset is a lot easier. Okay. So everybody okay on up counters? Pretty straightforward. Not much to them, right? And you can see why industry likes to keep up with stuff that they do, right? So you'll run into counters. By the way, in advanced PLC, the problem we have with these counters is these are softwares. So basically, every time you insert one of these instructions inside your program, there's a little subroutine put inside your machine code program that handles counters. And it's software, guys. The biggest problem we have with software is that it never can be as fast as hardware. But the nice thing about software is you can change it. So what's your PL? But if I had a motor running 7,200 RPM and I had an encoder out there trying to figure out how fast it was going, these guys won't have a chance in hell of keeping up with that. And they realize that. So what did they start doing? Well, what they do on every PLC you buy now is they'll have a high-speed counter that is hardware supported. They have hardware counters inside the PLC that you can use. And you would use those for these motor speed encoders and stuff like that. Encoder gives us the speed of the motor and also gives us position. So robots have encoders on them. And them robots, you seen robots? They move pretty fast. I wouldn't do that with a software counter. So this is the big problem we have. So this guy would tell you how fast it could count. So in advanced PLCs, we'll show you how. So you don't have a hardware high-speed counter instruction. You got instructions where you initialize it, right? And then how you access when it's done. So this is the software. Everything we're looking at now is software. Okay, so let's look at our down counters. We can use the done bit, normally close, normally open, and everybody okay there. But anything we do, we got to do what? So this is what's weird about the Allen-Bradley counter. The accumulator decrements whenever the counter input device changes state. The preset value for the countdown usually is a negative number. Contents of the accumulator register decrements from its initial value of 0 to the negative preset number. The done bit is true as long as the accumulator value is greater than the preset value. Done is false when the accumulator value is less than the preset value. Are y'all ready for this? Oh, yeah. And all I can say, guys, is I'm sorry. So let's go offline. Let's see if they'll let us change it right here. No, they don't. So we're still online. No, they won't. So we'll just delete it. And then we'll put a down counter here. Okay. And we'll call it the same thing. That way I don't have to change my reset. C5:0. Okay. We got a value of 10. So let's leave the value of 10 in there and see what it does. Okay. So let's see. Let's download it. Okay. I didn't want to do that. Then I got to go online to get this thing over here. Okay. So what's the problem? Well, it'll have to roll all the way around. This one won't do it. So it's counting down. So your accumulator started at 0, and it's going the opposite direction, right? Okay. So we would have to count a long time, right? So let's go offline. So what we need to do, guys? No, we're gonna change the accumulator. We're gonna set the preset to 0, and then we're gonna set the accumulator to some negative value. Or did I do that, Mark? No, I think. No, that ain't gonna work. Yeah, so the preset is gonna have to be a negative value, and then we can set this to 0, right? That makes sense? Okay. So we're gonna load it with, okay, here we go. So let's go online, download it. Now notice the done bit is because my preset, my accumulator is greater than my preset because it's more positive, right? You understand that? Which is backwards in my opinion. And then when it meets the count, the done bit is going to turn off, right? I'm sorry, it's got to be more positive, yeah. So it's got to exceed it, yeah. And it turns off. And it's going to do what? It's going to keep counting down. And the only way I can do, the only thing I can do is what? Reset it. And then the accumulator goes back to 0. So that's why when you reset it, the accumulator goes to 0. That's why you got to load your preset with a negative number. That makes sense? So this guy here is going to be, the done bit is going to be true until you exceed your number, right? You understand that? Everybody okay? Well, if you're not, that's the way it works. So we could do things with this, like, I might keep up with my rejects. So I got one up counter counting them when they come by, and at the end one, I got a down counter counting when they go off the end. And as long as they equal to 0, then what does that mean? I had no rejects, right? As long as my input and my output match. So we use these all the time. Probably up counters is probably used a lot more than down counters are. And like I said, Allen Bradley does not support, or the RS Logic. I don't know about the RS Logic 5000. I can't get it to connect to our PLC right now. We got some compact logics which run on RS Logic 5000, but the version of 5000 that we have does not support the PLCs that we got. So I'm having to deal with that. If I can get that done before the end of the semester, we'll bring it over here and show you all a little bit about RS Logic 5000. But your guides, you're going to notice they're almost identical. Almost identical. As far as the project tree on the left-hand side, but it might add more instructions. Instead of just having an up counter and down counter, it might have a up down counter. I know step 7 and also the TIA portal has an up down counter that's available to you. But anyway, so guys, what do y'all think? Let's make So it probably talks about countdown instruction, normally open input, comparison. We've already talked about that. PLCs, counter instructions. And some manufacturers, the contents of the entire section of a conveyor, and that's what we just got through talking about. So what they're trying to do is trying to keep up with what comes in over here does what, you know, and then they probably got the program that does that. Proximity switch. Anybody know what a proximity switch is? It lets you know when something's at a position. It's not a position sensor. It's what a proximity means. And a proximity means next to, but over time, proximity has turned out to be solid state, which means these are non-contact, what we call a non-contact sensors. Even though technically a limit switch is a proximity switch, they've got their when the first operating systems for these PCs that came out, they call them a disk operating system because they loaded off disk into the RAM of the machine. So they call them DOS. And then they came out with Windows. Well, the original version of Windows was a parasite operating system. It rode on top of DOS. And then they came out with Windows XP. Well, instead of calling it a DOS, they start giving them their name so people wouldn't confuse it with the original DOS that came out. So over time, the term proximity means these are solid state non-contact sensors. What do we mean by non-contact? They don't have to touch what they're measuring. So we have all types of non-contact proximity sensors that we use as counters. And we could have showed y'all some of those on the manufacturing line. Over there the other day, I should have showed y'all those that we could use as counters. Through the beam, what we call diffuse, retroreflective, we could use any of those as counters. We could use capacitive sensors. We could use inductive sensors. We could use anything as counting these inputs there. And do they talk about cascading? We talk about cascade. When would you need to cascade counters? If you need to count higher than 32,767, right? Or if you need, or less than that, right? You understand that you could cascade them. We usually did it in hundreds, so it was easy to keep up with. So this was your tens counter, and every 10 it would increment your hundreds counter. Does that make sense? And or you could go to thousands, and that's what we used to do. But you can cascade these timers, and all you see is you use the what? Just use the done bit. And then, by the way, you can reset both counters at the same time. You can parallel them, right, because they're outputs. So you can put multiple parallel circuits and reset. You can reset all your timers and everything at the same time. And there's other neat ways you can do it, but we don't. Well, as far as the registers, you have the preset register. So timers, we have the time base. And so I think what you're going to find out if you're on one of the 1000s, I think you only got one time base available. I think it's 0.1. The 1100s, I think we have three time bases available, or three multipliers available. In fact, that's what we was using a while ago. I think it's got three. Logic Pro only has one time base. But as far as your accumulators, they have basically the same function, right? And your preset registers have basically the same function. But you got to understand, guys, is those presets and those accumulators are addressable, which means what? You can put a constant in there, which is what we're going to do this semester. I don't think they are, or we can put a what? We can put a variable with a move instruction. Just move something from here into there. So I could take the output of math instruction and load my preset register with my counters on there. I could do so we'll look at more of that when we get into advanced PLCs. So what we're doing here is we're doing basically when the PLCs first came out, this is about all they would do, is go through counters and timers. But what they realize is these guys are computers, right? So what can they do? They can do logic, they can do math, they move stuff around. Well, you'd be surprised how much a computer just moves stuff around. And just by updating the display on your screen, how much data has to be moved around to go from the RAM in your machine to the video RAM on your video card. So one of the big tasks is just moving stuff around. And so that's as far as we're going to get in this semester here. Is the move instruction we're using is just going to have two constants that we can load in to treat as variables, right? You understand that? So any questions? So we're going to make sure we do the timer labs and the counter labs, which are your 8s and your 9s. And then I want to make sure we do the force lab and also the latch and unlatch lab, whichever one that is. So what I want y'all to do is wherever you're at, when you get through the lab you're on, do those. Do what? The force and the latch and unlatch, whichever one that is. And then when you get through with that, do the what? Timer and counters, and then drop back to wherever you're at. Everybody okay? So any questions? Good, great. Rich let y'all out early tonight. Y'all go stand out in the parking lot and bump into cars, right? Of course, I can open up the lab back there if y'all got